We now look at something called the Euclidean algorithm, which helps us find greatest common divisors of difficult numbers. So we're going to start by looking at greatest common divisors where factorization of the numbers is difficult, so we can't use prime factors. Next, we're going to look at the quotient remainder theorem, and we're going to use it to turn very hard greatest common divisor problems into slightly easier ones. Then we're going to use that to develop the Euclidean algorithm and demonstrate it on a particular greatest common divisor. So let's look at this problem, which was the last one on the greatest common divisor problems that you just did. This is not a very pleasant GCD to find. Factoring is difficult, so finding a prime factorization is very hard. And so the question is, can we compute the greatest common factor without factoring and without trying every single number between, 1 and 9,702? That would not be fun. Well, let's see what division does for us. Now, if we do the division of 25,410 divided by 9702 with quotient remainder, here's what we get. We get 25,410 equals 9702 times 2 plus a remainder of 6,006. Let's see what we can do with this. Well, let's suppose that D is a common factor of 25,410 and 9702. This is going to be important if we want to know what the greatest common factor of those two numbers is. Well, if we take this equation and then divide both sides by D, we get something like this. And now what I want to do is I want to isolate that 6,006 over D, so I'm going to subtract that 9702 times 2 over D from both sides, and we end up with 25,410 over D minus 9702 times 2 over D. Now remember, we know that D divides evenly into 25,410 and 9702. That's just what it means to be a common factor. And what that tells us is that 25,410 over D minus 9702 times 2 over D is an integer. It divides evenly into the first term. It divides evenly into that 9702, so when we multiply that by 2, also an integer. So everything's an integer there. We subtract two integers, we get another integer. But since that's equal to 6,006 over D, that is also an integer, which tells us that D divides 6,006. Now, that's a lot of stuff going on, but if you want to summarize what we just did, if D is a common factor of 25,410 and 9,702, then D happens to be a common factor of 9,702 and 6,006. Right? It divides evenly into both of those numbers. Well, let's try it the other way around. Suppose now that you have a common factor D of 9,702 and 6,006. Well, again, I'm going to divide both sides by D, and now I'm not even going to do any algebra. D divides that first term because it divides evenly into 9702. It divides the second term because it divides evenly into 6006. And that tells us that adding them together will give you an integer, but that also means that 25,410 over D is an integer, which means D divides evenly into 25,410. And that tells us that if D is a common factor of 9702 and 6006, then D is a common factor of 25,410 and 9702. So, well, who cares, right? Well, that tells us that the common factors of 25,410 and 9702 are exactly the same as the common factors of 9702 and 6006. And if we can be a little bit clever about that, that tells us that the GCD that we were looking for, 25,410 and 9702, is exactly the same as the GCD of 9702 and 6006. And that is actually significant because that second GCD is taking the GCD of smaller numbers than the first one. So we've taken a GCD of two really big numbers and replaced it with a GCD of slightly smaller numbers. Well, they're still pretty bad. I understand. 9702 and 6006 those are pretty big numbers. So you might wonder, well, how are we going to find the GCD of that? Well, we're going to find it exactly the same way. we're gonna do the quotient remainder on that one. We get a quotient of 1 and a remainder of 3696. Play the same game. We find that the GCD of 9702 and 6006 is exactly the same as the GCD of 6006, 3696. Again, we've converted the GCD into the GCD of two smaller numbers. Still pretty big, but you can imagine where this is going. If we keep repeating this process, we can keep on getting smaller and smaller numbers until we finally get numbers that we can deal with. All right, so let's summarize our work so far. So what we have is this theorem, and we just did it for that one particular example, but this certainly works for any integers. So if a and b are integers, and if we do a quotient remainder on a and b, so if we write a equals bq plus r for some integers q and r, then the GCD of a and b is the same as the GCD of b and r, and recognize that b and r are smaller numbers on average than a and b are. And if we apply the above theorem recursively, in other words, if we go through this process over and over again till we get a GCD, that is called the Euclidean algorithm. So if we apply it to the problem that we were just doing, we already did the quotient remainder on that, right? So we get 9702 times 2 plus 6006 equals 25410. And so that means that we get the same GCD for 9702 and 6006. And when we use the quotient remainder on that one, we get 9702 equals 6006 times 1 plus 3696. And so that gives us the same GCD for 6006 and 3696. We keep on going, right? So 6006, 3696 gets converted to 3696 and 2310. We use the quotient remainder on that one. 3696 and 2310 get converted to 2310 and 1386. Goodness, we're almost finished with this one. We do it one more time, I believe, right? We get a quotient of 1 and a remainder of 924. So our new GCD, same one as before, but with smaller numbers, 1386, 924. I lied, we're going to do one more. Then we end up with 1386 equals 924 times 1 plus 462. Our new GCD is of 924 and 462. And finally, that one divides evenly. 462 times 2 equals 924. So we get a GCD. Well, so our original GCD is equal to the GCD of 924 and 462. Since 462 divides evenly into both of those, that gives us a GCD of 462. So you can see, I mean, we had to go through a lot of steps, but we were able to, without knowing any factorizations, just doing quotient remainder, figure out the GCD of those two numbers. All right, so I think you're ready to go ahead and try the class activities on those. It's on the PDF included with this video.